My name is Dr. Shobhu Sachisyan. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, first and second year. So now here I am talking about my second year courses, which is called Physics II courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bouquet is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, we have added the topics. So the idea is that it is tailor-made for you. It is made for you only. Okay, what is needed? Okay, for you. You know, all these things you are doing because you, as a computer science and engineering students or information technology students, when you will be passing out, as per because our college is NBA accredited. Okay, some of the courses. So as per the requirement of NBA, you are in an outcome-based system. As NBA guidelines suggests, you should be coming out with 12 attributes, which are called program outcomes. Okay. So now those program outcomes you attend to variety of courses. You'll be in every semester you have got 5 papers. So at the end of each semester, you'll be passing actually coming across almost 35 to 40 theoretical papers, depending on the course. So there are 2 physics courses. Now these courses are there to attend some of the program outcomes. So our course have got some course objective and obviously some course outcome. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics. Okay, is to apply quantum mechanics for learning the latest of computation called quantum computation. Learn quantum logic gates. Is to, as a student, you comprehend about the hardware sectors of your devices. Okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course, and also this entire communication system. Okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE and IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design and for the storage material, that is the ideas of nanomaterials. Okay, so this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. Okay, thank you. Hi, hello. Welcome to the day 2 of my quantum mechanics courses. And as you know, today I am going to penetrate deep into the quantum mechanics studies. I will be talking about the probability interpretation, the wave nature of the matter, a matter as a wave of probabilities. But to discuss it, we need to learn a bit about your basic first year knowledge. What are the main concept of first year? How everything evolved from those wonderful experiments between 1900 and 1927. So, what is the outcome of all those experiments? Because those outcomes are needed today. They are going to give me the fundamentals of whatever we'll be learning now, the wave interpretation. Yes. So, let us get into the business. So, let's be again in 1900. Okay, and you see who is waiting for us. Mr. Planck. Mr. Planck is there. Okay, he is the main person behind the origin of quantum mechanics. So what Planck told, let us know it. So here is Mr. Planck. Now, to highlight about whatever you have been talking about in first year classes, I actually in first year I spent my entire class in talking about some stories. A story of 1900 to 1927. Few experiments was done, and each experiment was giving all of us, as a matter of fact, was touch of new physics. And it all started with an experiment that was explained by Planck in 1900, and that is the experiment of black body radiation. So what was done in black body radiation experiment? As all of you know, this is just a quick reminder. A black body is a body which can absorb any radiation at a low temperature of any wavelength incident upon it, as you could see in the picture. And if you heat a black body, it is expected to emit radiations of all possible wavelengths. For example, if you heat a piece of iron rod, okay, it will become reddish. But a red hot iron is not a black body because it only emits red light. If you heat it further, it becomes white hot. It is also not a black body because it emits only white light. I can call a body black at a higher temperature if it emits all types of radiation. For one classical example, maybe a bulb, okay, filament bulb is expected to act almost like a black body, but the ideal black body at a higher temperature is obviously the source of all types of energy, the sun. So at a low temperature, a body is black because of its ability of absorption, and at a high temperature, it will be black because of its ability of emission. And it is expected, ideally, a black body should have 100% ability of absorption. That means any radiation of any wavelength incident within it will be fully absorbed. And if, on the contrary, if you heat a black body, it is expected to emit all types of radiation. So at a higher temperatures, its ability of emission should be also 100%. Now, what was done? An experiment was done actually. A black body was heated. And due to the heating, what happens? It was emitting power, as I mentioned, because at a high temperature, it is expected to emit all types of radiation. In first year, I explained one experiment where energy for each and every wavelength emitted was plotted in it, and it was a graph like that. You can see on the picture was appearing, and it is changing because it depends on the temperature. Okay, the maxima will be shifted towards the origin as you keep on rising the temperature. It was resulting in a law called Wien's displacement law from the first year classes, But those things are not important today. What is important today is that how Planck explained the graph, because this experimental graph was not explainable easily. So physics was in a soup. Okay. So scientists tried to explain, because this graph has got a peculiar tendency. Okay, sometime it increases, for a small lambda it increases, for high lambda it decreases, in between it passes through maxima. And the beauty was that because it is plotting the energy emitted by a black body against wavelength, if you calculate the area under the graph, you expect to get the total energy emitted by a black body. Problem that scientists face, that it's a common sense, if you have to calculate the area under a graph, you have to do an integration over the wavelength. But problem is that, so it will be an integration like this. Okay, it will be an integration like this much. Okay, just like this much of integration you have to do. Okay, almost like this, an integration like this. You have to integrate the E lambda. Okay, E lambda should be integrated over the wavelength over d lambda. Okay, and problem,
and it will be integrated all over the wavelengths, because wavelength is emitted. All types of wavelengths are emitted between 0 to infinity. All wavelengths are emitted out by the black body. All types of wavelengths are emitted by a black body. Problem is that you can't integrate the more unless and until you know this E lambda. And problem is that this graph is not a straight line, so that you write down the equation of a straight line. This is not a circle, this is not a parabola, this is not a hyperbola. This is an unknown graph. So scientists face similar problem 120 years back. So they tried to get a correct expression of E lambda, because without knowing E lambda, you can't integrate. That is a basic job of an integration. Now the question is that if you can't integrate, your this experiment with black body radiation remains incomplete, because you cannot calculate the total energy emitted by the black body. So the problem is that you need a simple integration, but you can't do it because you do not know the functional form. You do not know the formula of E lambda, so you need it. So what scientists did, they tried to, because it's a graph, it's a curve, they tried to propose various mathematical expression. Rayleigh Jeans, first Wien came into business. He correct is that proposition was not right. Then another two scientists, Rayleigh and Jeans, came into business. Again, that was also not right. Okay, so what they did, the problem was that Rayleigh Jeans could not come up to the occasion. Wien could not come up to the occasion. So what is the proposition? Prescription is that everybody failed, so Planck has to be in business. So what Planck did, it's a whole, it's an entire story I told you in first year. So what Planck did, he made a simple idea. Before that, religions made a lot of wonderful assumption, but ultimately could not be successful. So in the explanation of this experimental graph, Planck made a wonderful assumption that energy of an object is discrete, is not arbitrary. It's like this. Okay, energy of an object is not arbitrary. You can see any people earlier thought any object can have any energy. Okay, but Planck told energy of an object should be something very specific, and it will obey a law, that is, it will be multiple of a quantity called h nu, where h nu is called quantum of energy. So this is the contribution of Planck in the development of physics, or development of quantum theory, I should say. That Planck is the first person in Earth who told energy of an object could be discrete. Before that, before 1900, because Planck told it in 1900. Before 1900, people thought any object can have any energy. For example, gas molecules are moving in a container. Their energy is like 3 by 2 kT, where 3 by 2 is obviously 3 and 2 are numbers. K is the Boltzmann constant, and T is the temperature of the container in which the gas molecules are moving. Now, idea is that so the energy of the object depends on temperature, and temperature can be anything. Keep the gas molecule at any temperature between 0 and infinity, and it is expected that should have any energy between 0 and infinity. Now, what Planck is telling, he's putting a restriction on that idea, that energy of, even we'll see later on also, energy of an object, in that case gas molecules, okay, it cannot be arbitrary. It should be something specific. It should be something discrete. That is the idea of Planck. He's the first person in Earth to think in a different way. He is the first person in Earth to challenge the prescription of thermodynamics, prescription of classical physics, that energy is arbitrary. He told that energy of an object in this discrete. Just try to think about the power of thinking of Planck. Before that, everybody knows the energy of a gas molecule is maybe 3 by 2 kT, coming from kinetic theory. Energy of a harmonic oscillator, maybe half of m omega square s square, which you know from classical physics, where m is the mass of the object, omega is the angular frequency, A is the amplitude. And so if you have got a pendulum oscillating, it depends on mass, it depends on amplitude of vibration, and frequency, the omega, angular frequency. Now, if suppose I've got suppose 20 pendulums, so, and they are vibrating with 20 possible frequencies, so their energy can be anything between those, depending, their omega is anything between that 20 values, and their energy can be anything. okay, depending on the value of omega. And suppose all of them have got same mass, same amplitude. The idea is that there is no restriction. It all depends on omega. If whatever be the omega is, it should be the corresponding energy. If I've got infinite oscillators, vibrating with infinite possible frequency, so their energy may be infinite possible values are there. So Planck is a person who is thinking, no, these arbitrariness should be removed. And that is a contribution of Planck in the development of quantum theory, that energy of an object is discrete. Okay, so when you move forward, this is something we should take into our pocket. Okay, so today when we are revisiting these studies, so this is the point to be noticed very carefully. The Planck's contribution to the development of quantum theory is this simple idea: energy of an object is discrete. Later on, Einstein taken up the idea that energy of a piece of light called photon is like multiple of h nu. Similar idea, but he has to think 5 years later from Planck. Planck is a pioneer. He told in 1900, energy cannot be arbitrary. It should be specific. It should be discrete. It should be multiple of h nu. H nu is called quantum of energy. Later on, Bohr taken up the idea. Bohr told that energy levels of electron in an atom are discrete. Okay, so Planck is a pioneer. Planck's idea came in 1900. That's why 1900 is also the birth of quantum ideas. So now to move forward, to proceed forward into our discussion. So if you keep consider the idea of Planck, the pioneering idea of Planck, I should say that energy beyond the classical limit, his thinking, energy of an object is not arbitrary, not is discrete. So physics, therefore, thereafter was divided in two parts. The physics from 1900 is modern physics, okay, and physics before 1900 is classical physics. Classically, the classical physics is the physics people learn in the 10th standard, 12th standard courses, where you mainly learn mechanics to learn about matters, and you learn wave theory, maybe light wave, maybe sound wave, to learn about the waves. So you divide objects into classes. Some of the objects are called matter, some of the objects are called waves. Now, if this pen is a matter, okay, this, suppose I've got another pen, this is also a matter. And this, how do you differentiate them? Suppose this is a pen and this is a small remote. How do you differentiate them? This is a pen and this is a remote. How do you differentiate them? The simple answer is that they look differently. So they look differently mean their geometries are different. This is like a cylinder and this is like a parallelepiped. So how do you differentiate the matters? This is a matter, this is also a matter. These matters have got different geometry. So they have got different size, different shape, they have different mass. So if I throw, they should have different momentum. These are the attributes of matter. On the contrary, if I consider waves, so light and sound, I cannot see light and sound. Okay, so they don't have any size or shape. Obviously, they don't have any light. You see, light is falling on my surface, on my hand. So I do not feel any pain. So it doesn't have a. So I am putting some sound on my hand. So I do not feel any pain for that matter. But I can feel it. That sound is coming on my hand. But I do not feel any pain. So light and sound do not have any masses. I cannot see also. Suppose a ball of sound is coming from my mouth, or a tube of sound is coming from my mouth. So because I cannot see them. They don't have any size or shape. So this is the other part of the story, which are called waves. No size, no shape, no mass, no momentum. You define them by some other parameter, wavelength, frequency, and phase. Again, this is classical knowledge, which everybody knows. This is the way people are dividing the entire physics. So you study mechanics for matters, which are described by this much of features, and you study wave theory for sound wave or mechanical wave, some type of theory for the elastic wave, I should say, or audio wave or mechanical wave, whatever you say. And for electromagnetic waves, light and sound, you've got some of the theory, but two different worlds. Matters you can see, matters have got size and shape. Matters means you define them by mass, momentum, size, etc. And waves are the other part of this story. No size, no mass, no momentum. Only you define them by wavelength, frequency, and phase. So two different worlds. Now this idea has to suffer a lot the moment you cross 1900. In 1900 and after 1900, two wonderful experiments was done. One of them is obviously photoelectric effect, okay, and another one is Compton effect. Now these two effects, I told you in first year, has changed the entire physics. that boundary that was imposed by Planck. Okay, so whatever is before 1900, all those concepts have suffered a lot. As we studied in first years, the moment to cross 1900. So this is and these are some of the attributes of matters. I'm just telling you the matters to have got masses, the momentum. So the best exhibition of material nature is collision. The waves they superpose. The best exhibition of nature is superposition. So when you learn normal mechanics, particle mechanics, the matter is a car moving, bus moving, train moving, they are colliding. This is the study of matters. But when you learn the normal the interference, diffraction, you learn this property of pure wave property, because interference means superposition of waves. And I told you several times earlier, matters can only collide. This is collision. Only matters can collide, because for collision, you need some momentum. Okay, for every collision, momentum is conserved. Okay, on the contrary, the only waves can superpose. Okay, matter cannot superpose. If you keep two matters in a position, before superposition, they will start fighting. Okay, that is called collision. On the contrary, if you bring two waves in a position, they don't have any momentum. So they can't collide, they will superpose. So best exhibition of wave nature is superposition, best exhibition of material nature is collision. Okay, and these are again the classical concept, but we should not never forget, even when you proceed now also. Okay, and these are and matter, and another important aspect is wave on a matter. For example, mirror effect, reflection. So if where a wave is incident on a matter, that is it's called scattering phenomena, and that you can see with the prism also. Now these ideas, as I was telling, is suffering the moment you are changing. Okay, you are crossing 1900. On this photoelectric effect, another is Compton effect. Now I just remind one of the issues of the what happens in photoelectricity. The entire story of photoelectric effect. Light was incident on a metallic surface. Electrons was emitted, but you need some specific frequencies or some specific wavelength, okay, called threshold frequency, above which you can see the entire arrangement in the picture there with yellow. Suppose I have got a metal, photoelectricity means I need a metallic surface. On the metal surface, light will be incident, and after that, electrons will come out. This surface is called a photosensitive surface then, but its sensitivity depends on the amount of on the intense of the wave frequency of the radiation coming in the picture. With yellow one, you do not get any electron emission. With green one, you are getting some electron emission. And there are a lot of studies that was made, and ultimately, how Einstein explained it. He explained it with photon concept, that it is the radiation coming in is basically the photons are coming in. Okay, I'll start with two assumptions actually. The incident radiation means it's a stream of photons, each having extreme amount of energy. That is, energy of the photon is specific, discrete. Okay, the idea of Planck is utilized. The energy of an object is discrete. And he also thought when photons are coming in, they are incident on one of they're taken up by one electron of that particular metal, and ultimately because of that, the electrons does come out. Okay, you just see the animation there. The photon is coming in, and it is taken up by electron, and ultimately because of the electron is actually getting out of the system. Okay. This is a beautiful animation. Okay, that it tells us that at a time, an electron can absorb only one photon. Okay, and after the absorption of the photon, if the energy is sufficient to overcome the attraction of the metallic nucleus, which is called the work function of the material, then the electron will be overcoming the Coulombic attraction and will go out, and that is a photoelectric effect. And this Einstein actually explained this with a wonderful equation, which all of you studied in the school level courses or even in the first year days also. This equation is called Einstein's famous photoelectric effect. But my objective was never to teach you the photoelectric effect. My main objective is to tell you that at least we have got an experiment where light is not wave, light is a stream of photon. Photons, I told you in first year, photons are like matters. Photons have got some energy, h nu. In first year, when we studied Compton effect, we calculated photonic momentum, h nu by c. In first year, we calculated photonic mass, h nu by c square. Somebody with mass and momentum is called a matter. Okay, I told you that we divide the object in two ways, waves and matter. So photons are like matters. Matter photon making collision with matter electron. and ultimately electron takes up the energy from the photon, overcomes the attraction of the nucleus and goes out. So the entire photoelectric effect, it teaches you a single lesson, that it is an experiment where light is not a wave. It is showing the feature of a matter. It is colliding. It's a stream of photons. Light is not like the wave we know. It's a stream of matter, stream of photons. Matter photon is photon is a matter with some energy h nu, momentum h nu by c, mass h nu by c square. These are all attributes of the matter photon. Matter photon makes collision with electron. Who collides? Matter collides. I told you a few minutes back, its collision is exclusively material property, superposition is exclusively wave property. So this experiment of photoelectricity is a clear signature of photons colliding with electron. So who collides? Matter collides. So what does it prove? In this experiment, electron is showing the electron is colliding with photons. So photons are like matters. Okay, and so basically that is the lesson of photoelectric effect. Planck told energy can be discrete, and photoelectricity is telling that next idea, that the wave that we know from childhood, light, it was reflecting, refracting, dispersing, so many interfering, so many things was happening. Now what you notice, it can sometimes collide also. Can it not? It can, a piece of light that is called photon. It can show the property of collision. Who collides? Matter collides. So it can show the property of matter. It's a whole new way of thinking. That is the beauty of Einsteinian idea. It's a Nobel Prize winning concept. That is a wave, a stream of known wave can show the property of matter. So if I now progress a bit, so if you see, if I now talk about light wave, okay, or for example, I am talking just about a light wave. It's basically it is true for any electromagnetic wave. Okay, if I talk about the light wave, you see in the experiment of photoelectric effect, it is showing the property of photons. Photons are like matters. Photons are colliding. Okay, it is showing the property of matters. Okay. On the contrary, in some other courses, when you learn reflection, refraction, dispersion, interference, same light shows the property of wave. Now, question comes in what light actually is, or what electromagnetic wave actually is. Is it a wave or is it a matter? So even if you ask light what you are you a wave or are you a matter? Even light doesn't know what it is. Problem is that in some experiments, actually most of the experiments that you studied, like reflection, like refraction, which are scattering experiment, like interference, like diffraction, which is superposition experiment, light is wave. It is scattering, it is superposing. But we can now see, we have in first year, we have seen actually two experiments, photoelectric effect and Compton effect. In both the experiment, light was exhibiting photonic nature. What photons are? Photons are making collision with electron. Who collides? Matter collides. So in those experiments, the same light wave is showing the property of matter. So question is that light sometimes shows wave property, or electromagnetic wave sometimes shows wave property, sometimes shows particle property. And problem is that you cannot use your photon concept in the expression of in the explanation of interference, because interference means superposition, and photons are like matters. They have got mass, they have momentum. Matters cannot superpose, because I told you superposition is exclusively wave property and collision is exclusively material property. So question comes in that when in some of the experiments where it is showing like interference, you cannot use photon concept. Opposite is true. Say photoelectric effect. If you try to explain photoelectric effect or Compton effect, I told you in first year, where X-rays were scattered and because of that wavelength of the X-ray was increased, modified. We are getting two types of X-rays at that time. So now if you try to explain photoelectric effect with wave concept, you cannot explain the origin of emission of electron, because the whole photoelectricity is a collision process between photons and electrons. So idea is that light is sometime wave-like, sometime matter-like, but you cannot use your material concept, photon concept in the interference classes, or your wave concept in the photoelectric effect or Compton effect courses. So light has got a peculiar behavior. Sometime it is wave-like, sometime it is matter-like, but it cannot show both the nature together. Now this peculiar behavior in physics is called wave-particle duality. Okay, this is called wave-particle duality in quantum mechanics. Okay, it's a wonderful idea, the wave particle duality. If you see I have presented something beautiful there. What light is? Is it a wave or is it a matter? The way we see it. Is it a wave or a particle? Okay, the answer is it is both. But light even doesn't know when it is wave and when it is matter. So two key things are there. The waves like light wave or in general electromagnetic waves has got a dual nature. Sometimes like photoelectric effect and Compton effect, it shows the property of photons, matters. And in occasions like reflection, refraction, interference, diffraction, it shows the property of wave. But problem is that when you are using photon concept, you forget the wave concept. And when you are using wave concept, you do not use photon concepts. So this is called wave particle duality in quantum mechanics, and it's a very important idea. And you see the entire idea of wave particle duality from the wave concept, uh, we have actually conceptualized. We have from by comparing some experiments. What I did, I compared your observation of interference class, diffraction class, reflection, diffraction, which experiments you have already done in labs. And I compared that with some other experiment, photoelectric effect, Compton effect. And then we came to the conclusion that it is sometime the light or electromagnetic wave, sometime photon-like and sometime wave-like. So it has got a dual character. Okay. So this is called a particle duality. So now to progress further, if you look at the entire story now, again that same old picture I am presenting, that objects, matters and waves. Okay, the two different worlds. Now to experiment, the experiment that I am presenting, photoelectricity tells me that a wave can be matter-like. Okay, that's the beauty of photoelectric effect. Okay, now then the concept of wave particle duality comes in, that light can sometimes be matter-like. Okay, in one line, photoelectric effect, the wave particle duality means a story of heat train. A non-wave is no more wave-like. It can be sometime matter-like. Okay, it can be wave-like, but there are occasions where it may be wave-like also. Now these ideas actually came up, okay, within a very short span of time, as I mentioned. Compton effect experiment was done in 1923 and photoelectricity in 1905. Okay, so from 1900 to 1923, within 23 years, physics has changed drastically. Now here comes another person into picture. His name is Louis de Broglie. What Louis de Broglie did, he observed this idea that waves and matters, okay, fine, they are there, okay, there are two different worlds as was thought initially. Now what photoelectricity is doing, it is breaking the jinx of classical physics. It is telling that a wave can be matter-like. Now de Broglie thought if a wave can be matter-like, the opposite should also be true. A matter can also be wave-like. Okay, now just think uh, with the power of imagination of de Broglie. He's thinking if light if can be photon-like, there should be some occasion. In photoelectricity, photon was colliding with electron. So electron is a matter, photon is a matter. Matter makes collision. What de Broglie is telling, there would be some occasion in nature where electron may be wave-like. Okay, that is his thinking. And that is that is the interpretation that makes the full cycle complete also. Earlier people thought waves and matters are different. Now we are getting some experiment like photoelectric effect and Compton effect which tells waves can be matter-like. Now de Broglie is telling the opposite. A matter can be wave-like. Now this is popularly known as the de Broglie hypothesis. And what de Broglie also told that, okay, fine, if a matter is wave-like, then it should have some wavelength, which is popularly known as de Broglie wavelength. It can be done very easily, okay, if you use the idea of photonic wavelength. Okay, from there you can calculate. Okay, now again it was a first year idea, but the idea is very important that de Broglie is telling a matter can be wave-like, and if it shows material property, it can be can uh, it should have some wavelength that is called de Broglie wavelength. So the idea is that if I just try to show you with a picture here, okay, uh, you can see here. The idea is that idea is this much. Suppose I have got a one-dimensional path like this. Suppose I've got a 1D path like this. I've got a, okay, just a second. I've got a one-dimensional path like this. Suppose this is x direction. This is x direction. Along x direction, suppose I've got an electron moving. Suppose this is my electron. Suppose this is the electron moving. Now electron is moving with, suppose electron has got some mass m. Suppose the electron has got some velocity v. It is moving with some velocity v. So it should have some momentum mv. And suppose this is the direction in which the electron is moving. So far, if you look at the description, I've got a matter is moving with some mass, some velocity, or some momentum. So I'm thinking classically. So it is expected if I keep another electron here. Suppose I've got another electron here. This is a second electron here. This is a second electron. Okay, if I keep a second electron here, so it is expected. Suppose second electron is at rest. Suppose it is at rest. So it is expected that this is the second electron. Now it is expected that the second electron, the first electron, will sometime, after some time, it is going to collide with the first electron. So for these two electrons, it is expected the first electron is going to collide with the second electron after some time. Now the question is that if you're describing the whole situation like this way, I'm thinking classically. Now suppose the electron is moving. Okay, now suddenly it gets a WhatsApp message from the electron. You now have to show the property of the wave. Okay, electron, you now have to show the property of the wave. Electron has to show the property of the wave. Okay, so this is what is telling. Electron need to show the property of the wave. Okay, electron, you show the property of the wave. Now this is something uncanny. I'm not telling electron will become a wave. I'm telling is thinking electron will show the property of the wave. It's a wave of what? Who makes the wave? That is something which will come up, which we'll discuss at the end of the discussion. But this is what is telling. Electron will show the property of the wave. This wave is called wave. This wave is called matter wave because it is representing the wave property of the matter. We'll discuss it in more detail very soon. Because it's a wave, it should have some wavelength. That is called the wavelength. And you can see some pictures are there. The wave property, wavelength of some of the electrons. Okay, electrons are there. Okay. So now, if I now move forward, okay, just a second. If I now move forward, you can see the animation there. Okay, the waves of electron, the waves of electron. Okay, beautiful animations are there. Electron waves are there, and you can see. I hope you can see those pictures. Okay, these are s orbital, p orbital, d orbitals of the electrons, and which you normally study in chemistry courses. So I told you in first year also, this SPD, this, when you think electron like this way, you're thinking electron as a wave. Now, and this contribution is, they tell it electron cloud, but it's not a cloud that will make a rain. It's a cloud of probabilities. Okay, I'll tell you very soon. So it's a wave of electron. Okay, and that is the proposition of de Broglie. Now the question is that if you look at the situation, what de Broglie is telling, okay, that for particle duality tells that for light can be photon-like. A electromagnetic wave can show the property of matter. De Broglie is telling a matter can be wave-like. Electron can show the property of wave. That wave is called de Broglie wave. As you can see it for electrons, I am showing there. Its wavelength will be called de Broglie wavelength. Now, you see what de Broglie is doing. It is ultimately at the end of the day, this is called it's an hypothesis. It's an hypothesis based on idea. So we need an experimental support of the Broglie, and I told from first year days. Okay, this experiment was done by two American scientists, Davison and Jama. So the Broglie idea was proposed in 1924, and within 3 years, in 1927, it was experimentally proved. Okay, the Davison Jama shown diffraction of electron. Okay, electrons, just like you do laser diffraction practically in first year physics laboratory. Similarly, where some red light passes through a grating, produces diffraction patterns. Here also, electron waves are sent through some atomic planes, and they make diffraction. They give diffraction pattern, and everything was explained with the idea that electrons are like waves, making superposition and giving some interference pattern. Okay, giving some maxima. So all those things we discussed last year and in first year classes, and the beauty of that, at the end of the discussion, electron wavelength was measured. It was like 1.6 angstrom, if you could recall. So wave property of electron, its wavelength, everything was measured in first year, courtesy Davison and Jammer. Okay, so we are now in a position to accept that if I that electron can show the property of the wave, and here our class begins. You should I would clarify one thing. I should make a bottom line of the class that in this year, in the second year quantum mechanics 2 courses, our class begins. Our starting point of the class is the Broglie idea. That in this class we talk about is the wave property of the matter only. A matter is going to exhibit the wave property. That means, in nature, four things can happen. A matter can show the property of matter. That means two matters making collision. Now, how two matters collide, that is Newton has taught you in school level courses. Second is that a wave is showing the property of wave. There is superposition that you learned in interference classes. Third is that a wave is showing the property of matter. That is the photonic nature, which you already studied. The photoelectric effect, Compton effect. Now, fourth occasion is what the Broglie is telling, the wave nature of matter. And de Broglie has already his idea has been proved also experimentally in Davison German experiment. So electron can show the property of wave. Matter can show the property of wave. You see, I'm not telling matter is a wave. I'm telling the matter can show the property of the wave. That is, electron can interfere. Electron can make constructive interference. Electron waves can make constructive interference. So now this is the beginning of our quantum mechanics 2 courses, the wave nature of the matter. A matter is showing the wave property. So henceforth, you should keep this line in mind. In our class begins with the Broglie. That is how we talk about wave property of the matter, and that wave is also called matter wave. Now, automatic question comes in, okay, fine, electron is showing a wave property, but it's a wave of what? Who makes this wave? It was a very interesting question. And this question is again coming back to your class now, because without reminding this, I cannot progress in my class. I have to tell you that it's a first year idea. Those beautiful pictures, animations you can see, that yellow, you see there is a wave moving. It's wave means it's a wave of electron. Wonderful animation is there. Electron wave is moving. Now, the question is that, okay, fine, it's a wave of electron moving, but it's a wave of what? Who makes that wave? It's a very important question. That is, I talk about wave property of matter, but it's a wave of which? What kind of wave it is? What I'm trying to tell you, by wave we mainly understand light and sound. Light means electromagnetic wave, sound means mechanical wave. Now I'm talking about wave property of matter. It's a wave of what? Matter wave. It's who makes this wave? That is a question we need to know now. We need to answer now, I should say. Now this answer is in the basic definition of wave. You see, that is just I'm trying to remind you. Wave means basically disturbance. Any wave means disturbance. Wave means fluctuation. Wave means variation. These are some of the common waves. Okay, wave. It's a wave of water. Wave of you see the who makes that wave? What is varying in case of water waves? The height of the water level. The height is varying. In case of sound wave, what is varying? These are some of the waves. Okay, disturbance, variation, vibration, fluctuation. So wave means some change. So any wave means something has to vary, something has to change. Now I'm talking about a new kind of wave, matter wave nature of matter. Question is that who is making that wave? Okay. Now in case of sound wave, who makes the sound wave? Sound wave is a vibration of the matter making the body. Okay. It's a vibration of the matter making the body. For example, if you clap, suppose you clap it. Who is making the wave? I'm generating sound, but who is making the sound wave? My hand, the matter making my hands are okay. They are doing this one. Okay, who is making the sound? The matter making my body is this the hand. My hand is vibrating. Okay, if I do this much sound you are getting, but who is vibrating? The matter making this table and my hand, both of them are vibrating. So these are all mechanical vibration. Okay, and if I okay, so to make sound wave, something has to vibrate, but it is the matter making the wave, matter making the body. Okay, so vibration of the matter making the object that is vibrating. Another wave is electric waves, AC signal. Okay, the electric field is varying. Okay, electric field or maybe current, maybe voltage is varying. Okay, the idea is that to make any wave, something has to vary. Another wave is a magnetic wave. Suppose alternating magnetic field. Okay, something is changing. Okay, the magnetic uh, the magnetic field is changing. Okay, so something has to change. And another example wave is the light wave, electromagnetic wave. In this case, who makes the wave? The electromagnetic wave is a vibration of two things simultaneously: electric field and magnetic field. Both of them vibrate perpendicular to each other. Okay, and the electric field and magnetic field both varies against some vector k. But ultimately, here to make any wave, something is varying. For sound wave, it is a matter himself is vibrating. For light wave, the electric field and magnetic, both of them are vibrating. For electric wave, only electric field is vibrating. For magnetic, alternating magnetic field is vibrating for magnetic wave. So to make any wave, something has to vary. Now we are talking about the wave nature of matter. Okay, Dibroy is talking about a matter is exhibiting wave property. Division and German is proving that electron waves are making interference. They have measured the wavelength of electron. But it's a wave of what? Who makes the wave? Is it like light, where electric and magnetic field will vary? Is it like sound, where the matter himself will vary? Is it like AC signal, where electric field or alternating current or alternating voltage is vary? Who is vibrating? Who is making the wave? That is the question. Now, to answer this question, we get into the basics of quantum mechanics. Quantum mechanics means I am talking about tiny electrons. Electrons are vibrating. Okay. Small electrons are vibrating. It's a world of microscopic objects. So answer is that who is vibrating lies in the example. Because here I am talking about mini object, microscopic object, an electron orbiting around the nucleus or electron moving in a metal. And it's a common sense. Suppose I am asking you to describe the journey of electron or the nucleus, or describe the journey of the electrons moving in a metal. Now, your problem is that suppose I have got this this remote, okay, and it is to make this it is polymeric body, okay, it's a bad conductor, but it's an insulator, but new atoms are there, electrons are there, they are moving. But can I see the electronic journey? Is it possible? Not possible, because they are too small, too tiny an object. Okay, I may say, suppose this here electron is there, electron is there. I cannot. Okay, I can say there are crores of electrons are there. You may say there are tons of electrons are there. Somebody will say electron is there, proton is there, so many particles are there. But who can see it? Nobody can see it. And the problem is in the size. Size does matter here. Okay, problem is in the minuscule size of the object. So what the problem is that for the microscopic object, okay, as I mentioned earlier also, your main problem is in the size. So it might happen, suppose I'm asking you to describe the journey of an electron and the nucleus. Now, your problem is that electrons are moving and the nucleus. But electron is there, it is moving. I know there are so many electrons are there. I cannot, my problem, I cannot see it. For example, if you have to describe only one atomic journey of one electron, around the nucleus of a particular atom. For example, hydrogen atom, the single electron system. You know electron is there, but you cannot answer my question because you cannot see the electron. How do you know? But this gives some hint. Hint is that, you can see the picture. Suppose I have brought it the strongest of the microscope, but I know electron is orbiting around the nucleus. So I am not sure, I am not certain where electron is. So if I take a chance to find out the electron, chances will always change. Okay, for example, you see this picture, this will be giving you more clear picture. Suppose electron, you can see there, electron is moving, okay, around the nucleus. But what you notice, electronic position is always changing, electrons are moving. But if I ask you where the electron is, suppose I have given you the strongest of the microscope, problem is that because it is moving very quickly, very around the nucleus, the chance of finding the electron is there, but where the electron is, you could not be specific. Chance of finding the electron is changing. Some you see the spots there, the red spots, yellow spots. You can see electron is moving. So chance of finding the electron at a given position is always changing. Okay, always changing. Okay, sometime electron may be there or here like this. But you just see the picture. You can just show you some with some arrows here. Okay, okay, just a second. You may be seeing electron is there. You may be saying electron is there. Electron is there. Electron is there. Okay, I'm giving the arrows. Okay, electron is there. Electron is there. Electron is there. Electron is there. Like this. Okay, there's so many arrows I have given. Okay, problem is that, the it is always, if I now put the arrows here and if I now again now keep the animation on, you see the you see I'm keeping the animation on here. You see, the chance of finding the electron is changing. Okay, my arrows are fixed, but electrons are moving around the nucleus, so their positions are always changing. Electron is there, it is moving around, but you could not be you cannot be sure where it is. Okay, you could not be certain where it actually is. It is changing its position every time. So something is varying. Chance of finding the electron is, look at the right hand side picture, those red spots. Okay, okay, my arrows are different and those red spots are changing. Okay, what is changing? The chance of finding the electronic position is changing. You may say electron may be there or here like this, but so it's always changing, always varying. Something is varying. Sometimes it is there, sometimes it is close to the arrows I have shown here, sometimes it is moving away from the arrows I have presented there. So idea is that the chance of finding the electron is always varying. I cannot be, it is, and if some variation is there, that makes a wave. So here we are generating a new kind of wave. It's a wave of chances. All the dots you can see now, these are all the wave chances of finding the electron. Electron may be there, electron may be there, may be there. And chances are varying. Any variation is a wave. So this wave that we are talking about, it's a wave of chance of finding the electron. And you can see the picture. Somewhere chances of you look at the picture I've just shown there, something is changing, something is varying there. Okay, electrons are changing the position, and the moment I am trying to see, okay, what I am noticing, the chance of finding the electron at that particular position is changing. Sometime electron is there, sometime electron is not there. So if you look at the peak, sometime the peak is moving up, sometime the peak is moving down. Something is varying. What is varying? Chance of finding the electron at those particular point, particular position. If some variation is there, you see, you look at the picture, what I am doing, we are generating a wave. We are generating a wave. Any variation, any vibration, any fluctuation is a wave. And you see, just choose a particular point at a given point. Suppose this point. Suppose this point. I just choose a given a particular point. Suppose this point. Just choose this particular point. or this particular point, and you see at that particular point what is happening, the chance of finding the electron is changing. Any variation, any vibration, any change, any fluctuation makes a wave. So that is the wave of chance of finding the electron. Chance of finding the electron is varying. Chance in a better language is called probability. So at that position indicated by the arrows, probability of finding the electron is changing. So here I am talking about a wave of electron, but it's a wave of what? Probability of finding the electron, chance of finding the electron. So the wave we talk in a quantum mechanics course is a wave of probabilities. Light wave is a wave of electric and magnetic field. Sound wave is a wave of matter vibrating the matter making the body vibrating. And the electron wave is basically I cannot see the electron, so chance of finding the electron at a given point is varying. Any variation is there, fluctuation is there, any fluctuation, any variation makes a wave. Just look at the arrows. At a given arrows as I indicated by the arrows in the third picture there, the bottom picture there, at that particular position, continuously something is varying. What is that something? The chance of finding the electron at that point is varying. Any variation, any fluctuation makes a wave. So it's a wave of chances. Okay, and chance is called probability in a better language. So the wave I'm talking about in a quantum mechanics course is the probability wave. So this is the probability wave of the electron. Okay, so these are the probability waves of the electron. So more beautiful pictures are there. Okay, so electrons are orbiting. Those curves are basically, you see the many colors I have used there. These are basically not the electron. That is not electron. That is the probability wave of electron. So the quantum mechanics wave is basically the probability wave of the electron. Chance of finding the electron. Okay, these are the probability waves of electron. Okay, you see chance is varying. Okay, probability of finding the electron is varying. So wave or matter wave is basically probability wave, chance wave. In chemistry courses, in atomic structure, you learn 2s or these wave consider you learn about various types of electron waves, 2s wave, 2p wave. These are they are not electron. 2s means you are thinking about the probability of finding the electron over a sphere, over a electron cloud, over a probability of finding the electron over a sphere. 2p means that is a probability of wave of finding the electron. Electron may be there, but you cannot see it, maybe over that region. And when you do superpose hybridization, you consider you superpose all the probability waves. So electron may be there in atomic, particularly in organic chemistry. You learn it now. The variety of superposition, 2s, so sp hybridization. Superposition means hybridization. Okay, hybridization means you are superposing s wave with p waves. Okay, and you are thinking electron may be present over that particular region. So who superposes? Wave superposes. So this it's a wave of what? Probability of finding the electron. You are thinking electron may be present over that region like this. So the idea is that, so point to note is that wave we talk about in a quantum mechanics course is a probability wave. More pictures are there. You can see it is this new picture. Okay, that you see the matter is moving and those curves are there. Okay, that is the probability of finding the electrons at which space is changing. So the way we talk about in a quantum mechanics course is the probability of these pictures will be coming later on also when we'll be seeing solving some actual problem. Now it's very important to note you look at the picture. I've got a red ball moving there between in the picture A, and at A is changing. Okay, the correspondingly you see B, C, D, few pictures are there. This is one of the problems of quantum mechanics we'll be solving in our class. Okay, you see the corresponding wave also changes. Okay, so that is basically not electron. It is the probability wave of electron. Okay, now you see the waves are peculiar. Okay, you see if you look at the wave, say wave C and D, you notice sometime the that is who is fluctuating. What is the fluctuating parameter? That is a probability. But you see sometimes they are becoming negative. But you know in basic mathematics probability of cannot be negative. Okay, so to overcome the problem is that the fluctuating parameter is no more called, not just called probability, it is called a just a it is indicated just by a mathematical function psi. Okay, it's a function of position because you can see it is changing with position, and it's also function of time because everybody, the matter is ultimately these are all dynamics problem, and psi is just a function because it is, although I was talking about it's a wave of probabilities, but psi probability cannot be negative, but in general you can see it's a that fluctuation may be plus, may be minus. So psi, if you keep just consider it just as a mathematical function, it may be both positive, both negative, anything. But to represent the matter, that is the probability of finding the electron, it has to be positive every time. So what scientists thought, his name is Max Born, he told you do not rely on psi. Psi is just a function, let it be a function, just a form, the variable, the of the varying parameter of the wave nature of the matter. Psi, if psi is zero, there is no matter. If psi is non-zero, there may be a matter. But to know the where the object is, the probability of finding the electron, it is given by square of psi, square modulus of psi. This is called Max Born's interpretation. If psi square, mod psi square is large, electron will be there. And if mod psi square is small, electron may not be there. You see some more pictures, it will be giving you more clarifications. Okay, look at this, these beautiful pictures are there. Okay. Okay, you see the psi and psi square I have kept there. Look at the psi 1. Okay, you see psi 1 is becoming negative. Okay, but as I mentioned, if I rely on psi to know where the object is, because it's a wave vibration of what? Initially, with just 2 minutes back, I told you it's the chance of finding the electron is varying, but chance cannot be negative. But you see, curve is becoming negative. So to overcome the problem, the Max Born, who is a German physicist, he told that you don't rely on psi, consider psi square. Let psi be a function. We'll find out that function in a problem, but we'll take square of psi to get the probable position of the electron. You can see square is always positive. Okay, it's a wonderful demonstration of the entire situation. So now, as I mentioned, that the same thing is written. And another wonderful idea is that, okay, fine, at a given point, the chance of finding the electron is given by psi square. Okay, it's very good, it's wonderful. But what is the total chance of finding the electron over the entire region? The total probability, this is just an example. Suppose in a 3 boxes, 3 piggies, you want to keep 1 rupee coin. Chance of finding the coin in any one of the, you see it's green, blue, and pink is there. In one of the piggy is 1/3. But what is the total probability? It has to be 1 because it is in one of the boxes. Okay. So the idea is that total probability of finding the electron should also be 1. This is called normalization condition. Many wonderful ideas are there to interpret it. Okay, so suppose I've got this remote in my hand. What is the probability of finding this remote in my left hand now? 100 times you look at, 100 times you can see it in my hand. Now, what is the probability of finding this remote in my right hand now? 100 times you look at, 100 times you will see it in my right hand. Okay, so now you see, I'll do this much. What is the probability of finding this remote in my one of the hand? Probability of finding the remote in one of my hand is half because it may be in the right hand or it may be in the left hand. So right hand probability of finding the remote in my right hand is half. Probability of finding the remote in my left hand is half. But what is the total probability of finding the remote in this room? Half plus half is 1. So total probability has to be 1. Similarly, when the matters are also moving, somewhere the probability of finding the, suppose electron orbiting on the nucleus, somewhere probability of finding the electron will be high, somewhere low, but electron is there too. Total probability has to be 1. Okay, this is called normalization condition. So to note it, it's very important idea to conclude today's discussion is that I made a long journey starting from 1900s, starting from black body concept to the photoelectric effect to the concept of dual nature of radiation, sometime wave, sometime matters, an opposite idea. If wave can be metal like, matter can be wave like, the de Broglie concept, proof of the de Broglie idea, division-German experiment. Then electron is a wave, it's a wave of what? Answer is a wave of probabilities, wave of chances. Okay. Now I am telling a matter can be wave-like, so that is a wave of chances. If electron moves around the nucleus, that wave is the chance of finding the electron. Now that we represent with the function psi. Actually, the probability or chance of finding the electron is given by chi square, and total probability is 1. So you can, and these are some very good pictures you can see. Okay. Now the question is that suppose I have got an electron moving around the nucleus in a particular problem. I want to know the wave function of the electron. I want to know, calculate the probability of finding the electron at a given point. So obviously, first thing you need to know the function chi. Then you have to get chi. Then you take chi square. You can do many more things with chi. I'll see. Let's say later on. So next point of discussion is that how do you calculate chi in a real physical problem? Now wait a bit. Let me discuss it next class. Okay. Thank you. Thank you.